to again proceed to the next chapter on vector mechanics for engineers dynamics. Okay. So today I'm going to proceed with the chapter of kinetic of particles. Okay. So in kinetic of particle, we have three important techniques to be discussed. Number one is Newton's second law, and number two is energy work and energy method, and the third one is impulse. So as today, I'm going to look at the aspect of Newton's second law. Okay, okay, for here, again, we are using the book of Ferdinand and Beers, okay, Russell Johnson, okay, chapter 12. And what we have covered so far by looking the syllabus here is we have done the first part of it. This is the kinematics of particle. We have covered linear motion, collinear motion, relative motion, and independent motion, and we have done with our first quiz today. And today and the first few days for next week after the Merdeka Day, we are going to look at the chapter of particle, about Newton's second law, framework and energy method, and impulse momentum. Okay. Right. These are the content of what we're going to cover. A bit on the introduction, the briefing of Newton's second law of motion, then linear momentum of particle, then unit, and then equation of motion. Equation of motion for dynamics, especially for this chapter, is very important. Okay, equation of motion, draw the diagram, and then draw the kinetic diagram, find the dynamic equilibrium, and then we apply all of what we have learned earlier for equation of motion for different coordinate systems. Okay, different coordinate system. We have angular momentum of particle, equation of motion in a radial and transverse component, conservation of angular momentum. Okay, all right. For Subject 3, space mechanics, Kepler motion or planetary motion. This one is I leave it to the student to explore if you want to read further. If you are interested to do in aerospace later on. I think this one can read your same study. Okay. Okay, today we proceed by looking at the introduction of Newton second law. So Newton's second law basically is governed by this important equation, which is force, okay, equal to mass times acceleration. Okay. By having this particle, okay, force acting onto this particle of mass m, okay, is acted upon by a force F. Okay. The acceleration of the particle, okay, the acceleration of the particle must satisfy this equation, okay, which is force equal to mass times acceleration. Okay. Right. So when the body accelerate means there will be changes in velocity, magnitude, or direction. So the second law is required to relate the motion of the body to the force acting. This is the definition of Newton's second law. We put it in writing. This just now is by equation. This is by writing or sentence. Okay, the sentence. So we have if the resultant force acting on the particle is not zero, okay, this force, this resultant force can be summation of force here. A particle will have an acceleration proportional, okay, proportional to the magnitude of the resultant force acting on it, okay, and in the direction of the resultant force, okay. So the resultant force not zero, that particle will have an acceleration proportional to the resultant force. So this F is proportional to an acceleration, okay, and in the direction of the resultant force. So they are in the same direction, okay. This force and this acceleration, they are in the same direction, okay. This figure shows the particle, and then this particle has different forces acting, okay, acting onto it, okay. Yeah. So different particle. The particle, we have here different forces, okay, different forces acting on the particle. Okay, let's see here. Particle, we have force F1, F2, F3, okay, and then the next figure here you have different forces also, F1, okay. This is how we complete the summation of force, okay. Acceleration must be evaluated with respect to Newtonian frame of reference, okay, which is one that is not accelerating or rotating, okay. What happens if the summation of force is zero? Meaning go back to static, what we learned last time. The force acting on the particle is zero, particle will not accelerate, okay. It will remain stationary, okay, stay there, will not move, okay, or it will continue on a straight line at a constant velocity, okay. Okay, I would like to proceed. Next one, as I mentioned in the table content, we talk about linear momentum of the particle, okay, linear momentum of the particles, okay. For linear momentum of particle, we have here earlier equations, F equal to ma, okay. So here we have a summation of force, okay. So over here All right. Um, we proceed. Uh, so that acceleration, which is here, we know that acceleration is dv/dt. So we substitute this a to be dv/dt. Okay, dv/dt. And then we put this mv together. So this mv, let's see, put d outside and put this one in parentheses. So d ddtmv, okay, ddtmv, right? ddtmv equal to mv basically is we denote as L, right? We denote it as L. So when we denote as L, we denote as L. So it's going to be dLdt, okay? dLdt. So dLdt we can denote as L dot, okay, L dot, vector L dot, okay, vector L dot, okay, this is dot. So this L basically is what we call the linear momentum of particle. Okay? Linear momentum of particle. I repeat, this is linear momentum of a particle. Okay. With this concept is important when we proceed, when we are dealing with concept of 3D later on. Okay. Another important concept that need to be mentioned here also is about linear momentum of conservation principle. Okay. If the resultant force of a particle is zero, the linear momentum of the particle remain constant in both magnitude and direction. Okay. So this is what linear momentum conservation principle, okay, is about. Okay. So if the resultant zero, linear momentum constant. Constant in what? In magnitude and also in direction. Okay. So the importance of this slide is I introduce you the concept of linear momentum of a particle. Okay. And then we talk about rate of change of linear. Okay. So graphically, if you look at this figure, this figure, okay, we have the path here, we have the mass M, okay, the mass M, and then we have here MV, okay, this is MV, okay, MV is L. This MV is linear momentum of particle. Okay, this MV. Okay, this is the direction of MV. Okay. So in figure or graphically, this is how it looks. Okay. Again about the unit. Okay. The unit uh, for SI and also the unit for US customary. Okay. So there are four primary dimensions, okay, in this chapter. First of all, about force, and then mass, and then length, and then time. Okay, so four. So for force, this is force in Newton. Okay, this is force in Newton. And then we have mass in kilogram. Okay, and then we have the length of it. Okay, the length. Okay, the unit is in meter. Okay, then we have time, right? Time in seconds. Okay, so this is a four primary dimension. Okay, 3, 4, 5. So for this one, the base unit for SI, base unit for SI is 1 Newton. Okay, force equal to mass time acceleration. Our base is force time mass time acceleration. Okay, so the unit of force is in Newton, and then mass time acceleration. Mass is 1 kilo, and then acceleration is 1 meter per second square. And then the unit we have here is 1 kilogram meter per square. This is SI. How about US customary? Okay. Okay, for US customary. Okay, US customary. This is for US customary unit. Okay. For US customary, again, they have also have the base unit. So the base unit here, they use force. Force is in pound. IB, this is pound. And then they have length. Okay, length. You have to do the correction. The length is not in meter here. This is not in meter. The length is in feet. 1 foot, 2 feet. Okay. FEET, FOO. Okay. And then times. Okay. So the unit of mass we derive as 1 pound. 1 pound mass. Okay, 1 pound mass equal to 1 pound divided by 32.2 feet per second. Okay, 32.2. Okay, for US customary they have 32.2. Okay, and then they have here 1 slug equal to 1 pound divided by 1 feet per second square. So it's going to be 1 pound times S square. Okay. Okay, we have done this one, 1 Newton. Okay. And then here we have 1 pound meat, 1 pound, 1 pound mass. Okay. So the unit look at this is 1 pound. Okay, 1 pound. Okay, 1 pound. So 1 pound, 32 feet per second. Okay. Okay, now we look at this figure. Okay, I want to explain about this figure to show how we can use this unit and relate with the the value of acceleration. Okay, look at the first one. We relate with SI unit. Okay, now we relate with SI unit. For SI unit, I mentioned just now we have a 1 Newton, okay, 1 kilo, and then 1 meter per second. So if the block move to the right, you can see this is the mass. Mass is 1 kilo. Okay, we know that force equal to mass times acceleration. Force same this direction, acceleration also go to this direction, and the mass we have 1 kilo. So we have force 1 Newton, mass we have 1 kilo, and then acceleration we have 1 meter per second. Okay, this is the first one. How about if this block, okay, we release from certain position, certain height, okay, so it will have the gravitational value, right, which is A. Okay? So we have here force, which is the body weight, the body weight. Okay, body weight. We have here the body weight. Okay, we have body weight, which is 9.81 Newton. Okay, and we have acceleration here. Okay, we have body weight, we have mass, and then we have here acceleration, 9.81 meter per second. Okay, okay. So I finished explaining about SI. How about US customary? Okay, for US customary, we start from here. Okay, and we relate with this equation. We have 1 pound force. Okay, 1 pound force, and then we have acceleration, which is 1 foot per second square, and then the mass. The mass, we convert mass to be slug, equal to 1 slug. 1 slug is equal to 1 pound, okay, s square over. Okay, okay. Now look at the gravity. Okay. We relate with gravity. We have 1 pound force, and then mass is 1 pound, and then the gravity here is 32.2 feet per second. Right. This is about the unit. Next one, okay, for this chapter, it's very important for us to set up what we call the equation of motion. Okay, sometimes we write the equation, we write EOM. EOM is short form for equation of motion. Okay, so if you look at for equation of motion, we consider a particle of the mass. Okay, of the mass acted upon several forces. Okay, we have several forces. So by definition, Newton's second law, that way we defined earlier. We have here summation of force, okay, equal to mass times acceleration. Okay, underline. So I name this equation. Okay, so for this equation, summation of force equal to mass times acceleration. So for here we have the particle. This particle here we have two forces acting on this particle, this direction and that direction. Okay, and then we equate it to the right, which is MA. Here we have N, mass, and then they have mass time acceleration. Okay, mass time acceleration. Okay, so we relate this force on the particle and vector MA. Okay, all right. So we can relate this by looking at from different component. Can relate this
Equation of motion relate with a rectangular component. Yes, we can relate. We can also relate it with a tangential and normal component. Okay, and the one that we have discussed early this week. Okay. So we look at the first one. Okay, look at the first one, which is vector equation, okay, for rectangular component, okay, for rectangular component. So this force, we can resolve, okay, we resolve each force, and also the acceleration we can resolve into rectangular component, okay. So we can resolve it into rectangular component. This force we can write in term of fxi, okay, fy j, and then fzk, okay, equal to mass times we resolve into rectangular component, so it will be max, okay, max, may, and then az, okay, and then you can put all together, okay, in x, y, and z. So it's going to be summation of force in x direction equal to max, okay, this one, summation of force in y, summation of force in z, okay, and also we can write in this form, okay, which is ax basically is x double dot, okay, y is y double dot, and z is z double dot, okay. All right, we can also write in terms of tangential and normal component, okay. This one straightforward for rectangular component, okay. Now we are moving to the next one, how to relate with tangential and normal component, okay. Basically it's the same thing. So summation of force we can resolve it into summation of force tangent and summation of force normal, okay. So we have this equation, summation of force T equal to MAT, okay, summation of Fn equal to MAN. So basically what is MAT? So MAT basically is dB dt, okay, and then summation of force in normal is mv squared over rho, okay. It's nothing new, we do that, but the way we do the arrangement and relate with summation of force equal to mass times acceleration. So by looking at this drawing, we have the first figure here, which is a summation of force tangential, then summation of force normal equal to this is mass times acceleration. So we have mass times at, and then this is m mass times an, right? This is for the case of tangential and normal component. Okay, this one is about dynamic equilibrium. Okay, dynamic equilibrium. We have alternate expression for Newton's second law. Okay, I'm not going to do that. Okay. Okay, for this one, it's an example. Okay, example. we do this example. Okay, to strengthen the concept that we have learned just now. Okay, all right. Can you see this example? Please respond in our chat box. Can you see? Example 12.1. Okay. Okay, I give you 1 minute. You read the problem statement carefully. Okay. Read the problem statement carefully. Okay. So here, what do we have? We have a block. Okay, 200 pound. 200 pound block at rest, lay on the horizontal plane. So we need to find the magnitude of the force P. Okay, what will be the magnitude of the force P required to give the block of an acceleration? Okay, acceleration of, not or, acceleration of 10 feet per second square to the right. Okay, acceleration of 10 feet per second to the right. So the coefficient of kinetic friction between the block and the plane is 0.25. This is the coefficient of kinetic friction. Okay, mu s is 0.25. Okay. This is very straightforward. So what is our strategy to solve this problem? Okay. First thing, we need to write the equation of motion. Okay. Equation of motion of the block. Okay. And we write equation of motion for this block. Okay, we try to write equation of motion. We draw the block. Okay, two blocks, the summation of force, and also the kinetic diagram of it. Okay. Force diagram. So draw two on your own. Okay. Show me where is the force. Okay. Here. And this is the kinetic diagram. Acceleration diagram. Force equal to mass times acceleration. So on your left hand side, you put all the forces acting on the block. Okay. Then on your right hand side is the acceleration. Okay. And then also remember that this type of problem we talk about US customary system. Okay. So if it's in pound, it will be in feet or foot percentage. Okay. Yeah. So the answer will be in pound. Okay. Okay. And then another thing that is we need to look also after you resolve pressure motion of the block, okay, into two rectangular component equation. So you resolve, okay, and then you're going to see the unknown. Unknown consists of the applied B, okay, applied B and normal reaction A, okay, from the plate. So we need to solve the unknown. Okay. So the most critical part here is equation motion. To my experience, for this chapter, the critical part is the student should be able to write equation, do it right. Okay. If you start this one wrong, the rest will not, it's not counted or not accepted, not acceptable, because you start with the wrong equation. Okay. Then this is what I mentioned just now. We start with writing equation of motion. Okay. So we have the block. Okay, you push it to the right, from left to the right. Okay. So this force, and then we have the frictional force. Okay, frictional force oppose the direction of motion. And then you have normal force. This is normal force, and you also have a body weight. Okay. So we have this block. We have a frictional force here. Okay, frictional force. And then we have the body weight. Okay. The body weight, and then we have this P. This P you can resolve into X and Y. So you are given P cosine theta, P cosine 30 and P sin 30. So you can resolve the value of P. Okay. And then you can put together the summation of force in X direction and in Y direction. Okay. Summation of force in X and in Y direction. Okay. So we resolve the equation of motion. Okay. The two components, we have summation of force in X direction, F equal to MA, okay, and you have also, okay, we have also summation of force in Y direction, which is equal to 0. Okay, so we have here summation of X in MA. Okay, so you put all together, P cosine 30, okay, P cosine 30 minus 0.25, okay, this is frictional force, 25 N, multiplied by mass. So mass here, you have 200 pounds, divided by 32.2, you get 6.21, okay, and then you multiply by the acceleration of it, which is 10 feet per second. Okay. This is for mx. For my is n, which is we have n minus 200 pound minus in this direction, go this direction and everything. So minus p sine 30. Okay. So we have these two. And then you solve these two equations. I name this one as equation 1, this is equation 2. So you solving for n, okay, and then you get the value of p. Okay, get the value of p. So want to find the unknown. We have two unknown here with p and n. Okay, so these two equations we can solve. Okay, by using these two equations, so you get the value of P equal to 151 pounds. Okay. Then I'm going to stop here for today.
So I'll see you next one.
Sorry sir, I have a question.
Next question. Give two friction law and plate.
Sir,
Okay.
I have a question, sir.
All right.
If let's say the question it gave two friction. One is the friction of the block, and the other is the friction of the plane. Which one should be used?
Friction of the block and the plane.
Yeah.
This one is the coefficient of friction between block and plane. So we only want mu k. Normally, if they give to mu k and also another one is static coefficient. Okay. So for
Yeah,
that,
static.
so it have a different condition. If static, the block is not moving. If we talk about dynamic, the block is moving, so we use mu k. Yeah.
Okay, thank you, Doctor.